come here to this beautiful Cairo. I'm coming from different domains, from system engineering and automotive software. I would like to present in this paper some techniques that we have been using for communication and for understanding the models when you use a lot of tool chains. So today I will present a little bit the context of my talk, and I'm in model-driven system engineering context. Then I will go a little bit into the tool chain we are using a lot at the university to develop different digital twin application. Very shortly, approach and implementation. I will give you some examples, conclusions, and future work. A little bit about me, very shortly. I have been there for 32 years at the university, so I have a lot of experience with the industry and with the teaching. So my background, software engineer, visualization and virtual reality. I have a PhD in numerical mathematics, and these are the most important domain I'm involved at this moment: intelligent buildings, automotive, domotica, and digital twins. However, maybe you are a little bit surprised, but I must say I'm an evangelist from this point of view. I would like to, and I'm implementing the creativity course at the university. So as an engineer, you need to be creative, because otherwise we brainwash the students. I don't have time to elaborate there, but this is something related to the EQ development of an engineer, and we need EQ, not only IQ. So, model-driven system engineering context. I mean, you see all the people today, they talk about Industry 4.0. I will not go into details, but I want you to make I want you to be aware about one important aspect today in the industry. So we have to treat the complexity, all right? So we are starting from this cyber physical systems. We know what they are, but however, you know, we are building more and more complex systems. We are treating this complexity, tackle it in different ways. So we started with system engineering, we started with a model-driven, but now we are virtual engineering. And we have seen with Corona, I think this is a little bit the future. I'm sorry, what's a little bit the Dutch word? The future. I don't know, are you familiar with the digital twins? So this is the digital thread. I think one of the key speakers talk about it, but I think I am in the different direction here. When you have a physical entity, a system which is functioning, you build a virtual one. It's a twin of it. You collect data, because these physical entities and virtual, they have sensors and actuators. You collect data, digital data. You can apply AI here, and you provide services to the users. This digital twin can be used in the entire life cycle of the product. We call it digital thread. So I should say, have a look at this one, because this is the future. So there is one thing, how we can integrate all these components together, and how we can bring the engineers to have the same playing ground, so to speak, the same place where they can exchange data, where they can extract data. And, you know, I love the pyramids. They are very complex systems. You don't know how they have been built. You see? However, when we treat these complex systems, we have some aspect that you have to take into account: complexity, lack of understanding, and communication. So I am focusing more how we can communicate between engineers. Complexity we treated with the model-driven system engineering. I should say, have a look here about design thinking patterns. We should not reinvent the wheel, even in the software. So have a look at this one. You know, here is power of an engineer, because we have to integrate domains, but we should understand the domain at the level of the engineer problems that we have to solve. And there is an abstraction here, independent of the domain. So I should say, have a look here. Then communication. So in my approach for system engineering, we are using SysML. I don't know if you are familiar, of DSLs we develop ourselves for specific problems. So I am focusing here how we can capture the entire structure and functionality of a system with diagrams, graphically I can understand. Okay? You are familiar with V-model. So what we see is that at the left side of the V-model, we have the analytical concepts, I call it. So you have to understand, we don't talk about requirements, I'm sorry to say that, but capabilities, which contain requirements and the performance of that implementation of the requirements. So we have now a double V, so to speak, in the engineering. Here we have a virtual analysis integration where we use digital twins. We create virtual prototypes, we create models, and we integrate them before we go to the implementation here and we start integrating. So I should say, and even for the academia, have a look here at the virtual discipline in engineering, because we as software, we have to integrate these domains. So we will not escape to that. Then there are something that I am using daily. System engineering means a lot of tooling, all right? So you have to understand the problem, and this is a tool that I'm using, I should say, daily. We have, you know, doors for requirements. We have a modeler here. We have a publishing engine that I extract views from the models, and we do a lot of simulation. I am in automotive. I am doing the 3D virtual. I'm building the 3D virtual environment with Unity game engines or with Carla. However, we are moving also into the ROS. So the main idea is the following: how I can integrate all these models in one environment. I don't want to execute the models here, to simulate them there, to display them here. So it's very, very difficult. So we have here a development process. This is an example from automotive to give you an idea. So we have to integrate 5 domains. How we integrate them, how this guy will communicate in this environment. So what we want to do is that we need a system as a whole. I don't want to split domains. I have to analyze this whole in one of the tools. So what we have done is that we model everything with SysML. All right, so I can model the structure, I can model the requirements, constraint, allocation, and so on. Everything is there. So what we do, and what we like to do, is that I would like to get rid a little bit of the 2D diagrams. I would like to have the 3D diagrams because we understand better the 3D diagrams in a virtual environment. So what we want to do is that I would like to have a live link communication between these tools, and I place all the models in a 3D environment, okay? So the main question, the challenge is that how I can convert these models into a 3D and I can represent that inside the virtual environment. So we have 2 approaches. One is that, maybe you are familiar with this, model-driven, so we create models, and all these models are stored in the database. So our database, it's a Rhapsody database using SysML models. What we want to do is that how I can extract from the database the SysML information, I converting it, I create some Unity scripts, and I can display it in the 3D, together with a 3D representation of my digital twin. So it's easy here. We have API, we extract, we use CVS, we create some Unity classes, and then we import it inside the Unity game engine. But we have developed also a live link. We are working at this one. So what we want to do is that, picture the following. You have a tool in which you execute the models. You have a tool in which you display the 3D environment, and you have a tool in which you simulate things. So what we want to do is that from the 3D environment, I want to steer the execution and the simulation, and I want to see all the diagrams inside the 3D, that I can couple the CAD geometry of the specific component with this behavior and structure. Okay? So what we have done is that we use the web-based services. We have a publishing engine in Rhapsody, and we have a broker based on MQTT, and from there we publish everything in the Unity game engine. I will not go in all these details here. However, Let me give you, I have three minutes. I'm Speedy Gonzalez, don't worry. So in examples, of course, we started, with I can say, very simple diagram. So this is something we have created an architecture for autonomously driving truck. We extract all the information and we started with this, silly, maybe, but important for us, 3D representation of the diagrams. We have implemented 4 different diagrams: block definition, state machine diagrams, internal block diagrams, if you are familiar, requirements diagrams. However, we started more and more to integrate, and extracting data from here and populating, the diagram, even in a simple prototyping way. However, at this moment, we can export the diagram from the ABM Rhapsody inside of the 3D, and we can activate the behavior of the digital twin here based on the diagrams which is represented here. However, the best approach is for us this live communication, and we have a digital twin of a distribution center from the Netherlands. We have mock-ups scaled 1:30 ratio, and we have created a 3D environment. So what we can do now is that through the web services, we export all the diagrams from ABM Rhapsody, and we can interact inside the 3D environment, even using VR stuff, and steer the entire simulation. So we are on this road now, on this path of LifeLink, that we bring everything together. Even at this moment I'm talking, we have linked Simulink with the 3D, and we can export also from there all the models. So I think I have only 1 minute, I think. So we have created prototypes, and we are using this integration. However, there are some challenges that we are still facing. So we want to improve the 3D representation of the diagrams. We have a simple representation here. We need to test for large and complex models, SysML models, the entire system. So this will take a little bit of the time. And I don't know if you are familiar with level of details. So you can in VR, we can approach the diagram and you get more details. And when you have a bigger distance, you don't see the details. Okay? So what we want to do is that we want to bind the 3D representation with the CAD geometry. That I have an engine, for example, from the car. I select only the engine, and I can display the 3D models in the diagram, and I can execute them and see the behavior of the engine. Okay? So I move like Speedy Gonzalez through these 10 minutes. I hope that I triggered a little bit, at least the curiosity to look at the digital twins. So here we have a digital twin, and I think we'll offer a lot of perspective, cheap testing, but however, prototyping and implementing a lot of nice idea before you go to the real product. All right? So, questions? Yes?
Is this applicable to domains like automotive and manufacturing only? Or
No. It's everywhere where you have a mobile.
So domains like finance and banking?
Everywhere.
So how can you have this implemented?
It's very simple. It's very simple. Because we are talking about Industry 4.0, about sensors and actuators. Sensor doesn't mean it's a physical sensor. Sensor can be a point where you collect data in an, a company, in a group. So it doesn't matter. We're using here the abstraction of sources. So you can use this everywhere. This is my experience. And we have so-called knowledge graph. You cannot imagine how powerful, let me see, are this digital twin approach. And here is AI. Because you have data, I think it should be here. So your subconscious will memorize everything. Here. Here, there are companies integrating systems. You don't know the behavior of that system. It's a black box. But that system has an input and output. So you can control the input and you can collect. The most important aspect is here are the services. What do you offer to the user that the user can configure this one, and this one collect data, and here is AI, interpreting and finding aspects of the data. Here you can play back history data. I think this is the sky's the limit. And do not forget, these are connections. So we have tested that remotely. This part is in the cloud. This part, I don't know, is in Egypt. This part, I don't know, is in the Netherlands. So it's a distributed system. But it offers a lot of possibility even for academia to develop projects, you know, to test techniques. This is our experience, and this is, with COVID we had, I built a smart room. Yeah, so everyone was working in the smart room remotely. You have this one in the lab, so you can enter there and you can do your job. So I think this is the technology of the future. Okay, so we see it. Yes?
You mentioned the tools, things like requirement management,
yes.
These tools usually come from different.
Yes.
So do you have any pilots from?
Yes, we have it. We have it. But you have to understand one aspect. Let me go to the tools. There is an integration between the tools, because they are FMEI is, by example, used to export from here to MATLAB. But we have developed our tools and communication for Unity game and Rhapsody. So it's easy to extend with plugins the communication between the tools. I don't think this is the big issue. My experience is that how you integrate the entire stuff in one tool, that you don't have 20 displays to move, you know, it's one brain to control everything from there. So this is, exactly, so this should be here. Okay, but however, I encourage the academia to look at these tools which are at least free. This ABM they have an academic license, you know. This is free for the students. I think we have to buy this one, right? But this one are free. So I should, again, advise academia to look at these available tools and generate ideas. And I think this is state of the art for the students. And when they go to the industry, applying system engineering even for the software. Okay, so watch out about this part here. This part here should be well, let's say, here. Analytical concept. You have to analyze the problem. If you don't understand the problem, the water is rubbish. I'm sorry to say that. Sorry for my language. So we spend a lot of time here. And here we take the analysis of the black box system engineering. Inputs, output, threads, opportunities. But again, risk assessment. We do here to find the emergent behavior of my system before I'm starting there. But this offer me.
Sorry.
Yeah. Yeah.
With this kind of simulation and modeling, will it still be applicable to do test automation?
Yes. So for me, is to look at that. I started 30 years ago at the University of Eindhoven. I moved to all departments, and I see how they are brainwashed, but they are doing the same thing, you know? So if you stay at the abstraction level, you can instantiate this construction in every domain. This is my experience. All right? So, no. But there is one thing as an engineer. There are two aspects. One, holistic approach. It doesn't matter what you do. If I develop, for example, for the car, a model for a tire, what I've seen the students is going there. I say, no. Look at the stars. You have to start from the beginning, the car. You see? And then you find out the context in which you integrate that model. And this is something that we should learn as in academic, as engineers. You are not alone there in that model. Where do you use that model? And this we do here. I have to find out at the whole level is the thinking, not there. There it's a part of it, but you are above. Okay? I'm sorry.